To start section 2.7, folks, what we're going to do is we're going to talk about symmetry. So there's two types of symmetry that we're going to look at. The first type of symmetry is going to be symmetry along the y-axis, and then the second symmetry will be symmetry about the origin. There are two different types of symmetry in that the first symmetry is what we call line symmetry. So it is as if we could fold along a line and we're going to see some symmetry in the graph. The second one is a rotational symmetry, and so that'll be about the point of the origin. Okay, so let's go ahead and define a couple things first here. For symmetry, for y-axis symmetry, we call functions that have that particular type of behavior, we call them even functions. So if the graph of your function has this line symmetry along the y-axis, then the function that it's associated with is called an even function. So notice that on each of these three examples, and I went ahead and I listed what the function was that I entered into to create these. You probably haven't seen the cosine function yet, and that's all right. But notice that in each of these cases, I'm just going to zoom in a little bit here and take a look at these a little bit closer. So notice that, like in this first case of the x squared function, so everyone knows what the graph looks like of that. We've done it in class. But notice, again, here's our y-axis. So I'm just going to draw a dashed line along that. Notice that what we see on the right side is exactly what we see on the left side. So for example, if I'm over here at 1 over, if I'm 1 over, what I see exactly 1 over on this graph will be the same height as -1 would be over here. So these 2 points are mirror images of one another, and this continues up the graph. So like when we go over to when we go over to an x value of 2, we have a height value of 4. At -2, we also have a height value of 4. So just a couple things just to notice here. F of 1, this is the height. Remember, this is the y value of the function. So the height at 1 is equal to the height at -1. The height at 2 is 4. So this value is 4. That's the same thing as the height at -2. So remember, the f of these is the height value. Okay, these are the y values associated with these inputs of the x values. Okay, so notice what we have here. We have f of 1 is equal to f of -1, f of 2 is equal to f of -2, and it turns out that as we go on this graph, f of any of the positive values would be the same heights as the function at the negative values. Here we've got our absolute value graph. Okay, so again, when we go 1 over, we're 1 up. When we go -1 over, we're also 1 up. We go 2 over, we're 2 up. -2, we're 2 up. Because we go 3 over, -3 over. I mean, these are easy points to see on the graph. Again, we have that symmetry along this line right here. So again, we could go through, we could say, well, the height at, I don't know, let's say 3. The height at 3 is 3. So this value is equal to 3. Let me write that a little bit better. So the height at 3, which is 3, is also the same thing as the height at -3. At -3, sure enough, this is also equal to 3. So these are equal to each other. Or the height at 4 is this height. Well, that's the same height at -4. So I'm just doing a couple of them, but you can see that no matter what I pick for my x value, the positive will be the same height on the graph as the negative. In here, we've got the cosine curve, which a lot of you haven't seen yet, so I'm not going to go ahead and plug any values in. But again, so this is what we call a trigonometric function. So for those of you that are taking trigonometry next semester, you'll learn about this. But notice that, again, we've got this symmetry, this foldable symmetry along this y-axis line. Okay. So let's go ahead and talk a little bit about the algebra. So what I'm going to do is, in this class, in 0314, I'm going to talk about how you can show or you can demonstrate some symmetry with a couple points. Now, this doesn't prove symmetry. Okay, so I want to be very clear on this. In 1314, you're going to do a little bit different of a technique, and you're going to prove that something is an even function, or you're going to prove that something is an odd function, and you'll do that algebraically. What I'm giving you here is the foundations or the fundamentals, so that when you do that, that makes more sense. So we're not proving anything here. We're just talking about what should occur. Okay, so what do we have? Well, algebraically, functions that have this kind of like fold over symmetry along the y-axis, they have the following property. If f of x is equal to f of negative x. So when I pick, what this is saying is when I pick a value for x, if I plug in the negative, they should be equal to each other for any x that I pick. So for example, if I pick 1, then the opposite of 1, which is negative 1, well, these values should be the same. They should kick out the same height values on the graph. Okay, if I pick 3 for x, then f at negative 3. If I pick 3 for x, then f at negative 3 should have the same height. So that's all that this is saying here. Now, if this happens for every single x, not just the couple that we're going to check, but if it happened for all of them, then that is, if this part right here happens for all of them, then it's going to be an even function, and we're going to have symmetry along the y-axis. So what we're going to do is look at an example here. Let's say we've got this function x squared plus 3. Okay, now this is an even function. It's going to demonstrate this. So we're going to verify that for the different x values, 4, 2, and negative 5, when we plug them in, that it does work. Again, this is not a proof that this is an even function, but it's just a little bit of a justification for why we can possibly say that it is. So if we're going to check f, actually let me zoom in a little bit more for you guys here, make my handwriting a little bit nicer. So again, our f of x is equal to x squared plus 3. That's our function. Slide this down just a little. There we go. Okay, so there's our function. Now what we want to do is we want to check what is f of 4. Well, okay, let me write this down. We're gonna show that f of 4 is equal to f of negative 4. Okay, or we're at least going to try. Okay, given that this is an even function, that should work out. So f of 4 is equal to 4 squared plus 3. Well, 4 squared we know is 16, and 16 plus 3 is 19. So on this graph right here, if you went over to x equals 4 and you looked up or down, you would be looking up. If you're walking along the x-axis, you get to 4. Okay, like this. So our little guy's walking. He gets to a positive x value of 4. It's going to look up, and it turns out that way at a height of 19, he'll see a point. Now, if he walks the other way, so if he walks this way to negative 4, hopefully he sees the same height. So let's check. Well, f of negative 4, that's going to be equal to negative 4 squared plus 3. Now, we're taking negative 4 and multiplying it by itself. That's what this means. So in other words, we're taking negative 4 times negative 4 plus 3. That's all that this exponent notation means, right? We talked about that in class. So we've got a negative 4 times a negative 4. We know that's positive 16. And so sure enough, look at that. We get a height out of 19. So that's good. So we showed that at least for one value of x, that this graph has that characteristic where f of x is equal to f of negative x. So let's try some other points. Let's try 2. Okay, so again, we'll figure out what is f of 2, and then we'll figure out what is f of negative 2. So f of 2 is going to be 2 squared plus 3. That's 4 plus 3. That's 7. So again, if our little person walks over to 2, they look up and at a height of 7. So here's 2. Here's 7, not to scale. They look up, sure enough. There's the height of 7. Now what about at negative 2? Well, you can see here, you can already tell that when we square that negative, okay, it's going to become positive, and so we're just going to get the same thing that we did above. And sure enough, when you're at negative 2, you're also up at a height of 7. So now we've shown that this function demonstrates this even property for at least 2 values of x. Let's try a third. So here we have f of negative 5. That's going to be 25 plus 3. That's 28. And now we have to compare that to f of negative 5. Because our x value is negative 5, so now we have to do a negative of negative, so positive. And sure enough, that's going to give us the same thing. That'll give us our value of 28. Okay, so again, we have not proven or demonstrated that this is an even function for sure, because we'd have to demonstrate it. We haven't demonstrated that this function is even for every single x. We've just shown for 3 particular ones. And like I said, in 13-14, you'll talk about how to do that for every single x. Okay, so that is an even function that has symmetry along the y-axis. Okay, so line symmetry. Now we'll talk about odd functions. And odd functions, their symmetry is about the origin. So it's about a point. And what I like to be able to do is, or what I like to do is to demonstrate this is to rotate my image. And so I'll literally just take my paper and rotate it upside down. And what we're looking for is, do we see the same graph? Okay, so if we can spin our paper, when we spin it upside down, if we see the same graph that we did when it was upright or normal, then that graph demonstrates the function is an odd function, and the graph has point symmetry about the origin. So what does that mean? Okay, so let's go ahead and let's take a look at this function right here first. So this is the x to the third function. We're all familiar with that. Now, notice how on the left side we're headed downhill, okay? We go through the origin, and then we're headed uphill over here. Now watch, I'm just gonna take, so remember what this looks like. Now if we take and we just rotate upside down, if we just rotate it, do we get the same looking graph? Does this look the same? Well, yeah, it does, right? I mean, that's the exact same image that we just had here. Okay, so that is the type of symmetry that we're looking at when we talk about odd functions. Again, we've got this is the sine curve. For those of you taking trigonometry next semester, you'll talk about the sine function. Here's a partial graph of it. There's our origin. Again, what does this thing look like? If we go ahead and we spin it, do we get the same thing? Yeah, that thing looks real nice. Okay. And then, of course, the last one here. This is our cube root function. Again, we pass through the origin. That's the place that we're going to spin about. Take a look at the graph, spin it, same exact looking thing. Now, I want to point out, at least on one or two of these, some special points. So I want you to notice here that if I go over to 1, I have a height of 1 out. But if I go to -1, my height is -1 out. So in other words, f at 1, which is equal to 1, and f at -1, well, that's equal to -1. Okay? Or in other words, f at 1 is equal, I'm going to write it like this. In other words, f at -1, which is -1, is equal to negative f at 1. Okay, so it's kind of a lot going on there. So let's just go back through and do it a little bit more slowly. So f at 1 was a height of 1. Now, if I just multiply both sides by -1, notice that then this, they're both equal to -1. So then this would be equal to this, right? Okay. If I grabbed another point on here, this is harder to see because it's off the graph, but if I grabbed 2, well, we know that like f of 2, well, 2 to the third is 8. And then if we went over to -2, we know -2 to the third is -8. So notice that if I just multiply both sides here by a negative, then these are equal, which means these are equal. So in other words, f of -2 is equal to negative f of 2. So that idea, which I have written down right here, that negative f of x, negative f of whatever, is equal to f of negative whatever you plug in. If that's the case, and all of these graphs have that same property, okay, like if you go over this way, you go up. If you go that same distance over this way, you go that same distance down. So for example, if I walk this distance over, then the length that I go up would be the same as if I walked that same distance the other way, and then it'd be the same length down. Okay, so if I go over, up, it's the same as going left and down, or it could be the other way. You could go left and up, and then the right would be the same distance down that way. It wouldn't matter. So notationally, what we're saying is this should be true, that the opposite of the function, that this height should be the opposite of the function at this height. These should have opposite values. One should be positive, the other one should be negative, but they should be the same distance. So to justify that, okay, let's take a look. This function right here is an odd function. Okay, I've picked on this odd. We're going to verify for each of these x values, again, that this statement does hold true. So what we're going to do is we're going to take negative f of x. So negative f of 4. That's this piece right here. So I took my x value of 4, plugged it in, and take the negative of it. See what we get. So what we need to do first is we need to find f of 4, and then at the very end we're going to make it negative. So what I need to do is I need to take 4, plug it into f. So it's going to go here and here. And then when I'm done with all of that stuff, I'm just going to make it negative. So 4 to the third. Well, I didn't think about this ahead of time, so I think I can do that one in a minute. I think that that's going to be 64. So 64 plus 4, I believe, is 68. So this is going to be negative 68, or just negative 68. So what is this saying? This says that if we go out to 4, we would normally be at a height of 68. Okay, but the opposite of that would be negative 68. So that means that when we plug in negative 4 into the function, we should get out negative 68. So that's negative 4 cubed plus negative 4. Well, we know negative 4 cubed. Well, we know 4 cubed is 64. And then we have a negative times a negative times a negative. So that's going to be negative again. So this is negative 64 plus a negative 4. Again, that's negative 68. So it turns out that negative f of 4 is the same thing as f of negative 4. Okay, so let's go ahead and let's try what happens when x is 2. Okay, so what do we got here? So negative f of 2 should be negative 2 cubed plus 2, right? And that's our original function. So just plug it in. So it's going to be negative of 8 plus 2. That's the negative of 10, or negative 10. Okay, now what is f of negative 2? Well, that's going to be negative 2 cubed plus a negative 2. Negative 2 multiplied together 3 times, that's negative 8. Plus a negative 2. Sure enough, we know that's negative 10. So they're both equal to negative 10, which means these two are indeed equal to each other. So this property here holds. Let's try negative 5. So negative f of negative 5 would be equal to negative, and that'll be negative 5 cubed plus a negative 5. Again, I'm entering it into this f of x is equal to x to the third plus x. Okay, so they got to go on the both. So I have the negative up front. I'm just going to use square brackets instead of the parentheses because there's a lot of parentheses going on there, so this will make some more sense. So this is negative 5 times negative 5 is positive 25 times another negative 5 is negative 125 plus a negative 5, that is negative 130, or positive 130. So now what we have to do is figure out what is f of negative 5. So I have to take the opposite of the x value. Well, that's just f of 5. So we know that that is just 5 to the third plus 5. This is 125. And of course, we add those together, we get 130. So it does work out, okay? So what we're doing, again, we're just testing it with some numbers. Here, all I've done is just tested it with different numbers. Zoomed out a little bit farther, sorry. Tested it with some different numbers to show that, yeah, it is exhibiting these properties of being an odd function. But like I said, in 1314, what you'll do is you'll talk about how you do this in general, not just for specific numbers. So hopefully that makes sense. That's all I want to talk about in terms of symmetry. One thing I should mention real quick is that we don't test for symmetry on the x-axis. We don't test for symmetry up and down, because if you do have symmetry up and down, it's no longer, you're not working with a function, because you would fail the vertical line test. And so we don't talk about symmetry with functions. We don't look for symmetry we talk about the y-axis, but we don't talk about the x-axis because it doesn't make any sense if we're dealing with functions, that would automatically be a no-go because it would fail the vertical line test. So we don't look at that for symmetry. But that's all we're going to talk about for symmetry. Hopefully that makes sense. You should be ready to do some of the problems from 2.7 on symmetry. Next, I'll do a video on piecewise defined functions. So make sure you take a look at that link.